And now we enter into an analysis of RC circuits, resistive-capacitive circuits. So here we have a basic one with a source, a resistor, a capacitor, and a switch, and various points along the circuit marked off so we can specify what's going on. So initially the switch is open, everything is uncharged, and there's no current flowing in the circuit. And now we close the switch. There it is. Now initially, VBC, the voltage across the capacitor, is 0. Why is that? Because the charge on the plates is 0. There is no charge, therefore no E field, therefore no E field times distance, which would result in a potential difference across there. And then, as a result of that, there's no opposition to charge flowing onto the plates initially. No opposition. There's no charge separation, so charge has no trouble at all going onto the plates initially. So the initial current in the circuit is limited by the resistor. This does not offer any resistance. So I0, the initial current, is the maximum, which is VAB, the voltage across the resistor, divided by R, and that's going to be the EMF as well. So EMF over R. Now, that's initially maximum current. What happens after a long period of time? Well, after a long period of time, current is flowing onto the capacitor, building up the charge, opposing additional charges from going on. The electric field is building up across here, producing a potential difference, which is approaching the EMF itself, and the current in the resistor is getting less and less. So there's a Q over C voltage drop across the capacitor. And that continues on until it equals the entire amount, until the source cannot push any more charge onto the capacitor. So the voltage across the resistor just keeps going down, down, down. And then eventually it goes to 0. So the limit as time goes to infinity of the potential difference AB eventually goes to 0. The limit of the voltage across the capacitor as time goes to infinity equals the source. It starts at 0 and goes to the EMF. Now that's the easy stuff associated with this circuit, the initial and final conditions. Now we're interested in what happens in between those times with all the transients going on. So what happens at any time t? Basic idea is VAB equals IR. Okay? Voltage across the resistor. VBC equals Q over C, the voltage across the capacitor. And note that the small symbols, the small variables, I and Q, are time dependent, intermediate values. So we talk about big I, big V, big R. Well, R is constant. Large Q, cap Q, are the maximum values, and the small are intermediate values. So let's get the intermediate values for the current and the charge, and then the voltages as well. So here's our circuit, and we have a current flowing in the circuit that's a function of time, call it I sub t. The charge, because of that current flow onto the capacitor, the charge is rising, going up. So let's apply Kirchhoff's loop rule to this circuit, and we'll see how we can work with that. I'm going to choose a counterclockwise path around here. Starting at the switch and going around like this, we have EMF. We get to this point and we have a voltage drop, which is I times R. I is a function of t again. And then across the capacitor, plus to minus, it's a drop of Q over C. Intermediate value again. All that's equal to 0. So there's a little differential equation for us, as it will be. So what is the current? Current is, well, divide everything through by R, and then I gets by itself. We have EMF over R and Q over RC. So that's what we get for current, intermediate current value, where the initial current is EMF over R because Q is 0, so this whole term is gone. Now when I is equal to 0, after a long time, Q is equal to the maximum value, Q final, which we'll call cap Q. So then we have EMF when I is 0, EMF over R equals Q over RC. That's just this. If this is 0, this becomes this expression. So we can solve for Q, and it's equal to capacitance times volts, which we already knew from previous discussions. So now the current is dq dt by definition, and that's equal to EMF over R minus Q over RC. There it is. Right, there's our differential equation, which is V over R minus Q over RC. So I've just taken EMF and called it the voltage, the maximum voltage, across the resistor initially or across the capacitor after a long period of time. Now that's equal to, if we basically multiply V over R by C over C, we get VC minus Q over RC, which is dq dt. So now we can take the dq, divide by VC minus Q, bring that down here, and take this dt and bring it up over here. We get dq over VC minus Q equals dt over RC. So we see here that we've separated the variables and we have these differentials associated with the proper variables. In this case, we just have a constant. So that looks like something that we've seen before, at least that a similar form to that. Let's solve it. So now it's just a little bit of math. Let's integrate that expression we just had, the two terms. First one 0 to Q, second one 0 to T. Notice this is just a constant. So this is interesting here. So we have natural log, VC minus Q, and then this makes it negative. From 0 to Q equals T over RC, 0 to T. All right, so minus ln of VC minus Q, minus negative, when we put 0 in for Q, we have plus ln of VC equals T over RC. Natural log of VC minus Q, if you multiply by -1, minus ln of VC is minus T over RC. That'll put it in a better form for us, because now we have the difference between natural logs, which is the ratio, that's how I wanted it, equals minus T over RC. And what can we do with this? Let's get rid of the natural log by e'ing it. So that'll give us VC minus Q over VC is e to the minus T over RC, which is 1 minus Q over VC is e to the minus T over RC. And multiply it by -1 again, bring the 1 over on the other side. And it's just about the form we need, but I want Q. So let's multiply by VC. And we get our wonderful result that the Q is a function of time, is VC times the quantity 1 minus e to the minus T over RC. VC being the maximum charge that you can obtain in the circuit. 1 minus e to the minus T over RC. You should be able to think of what happens when T is equal to 0. Then this is just 1. 1 minus 1 is 0, so Q on the capacitor is 0 initially. When T goes to infinity, then that goes to 0. And we have Q becoming the maximum value, cap Q. That all makes sense, and it will also make sense in the intermediate values as well. Okay, we have the charge as a function of time. Now let's get the current as a function of time, recognizing that the current is dq dt. So let's take the derivative of the charge. Now notice I expanded it back out. We want to do that because the derivative of this constant is 0. So this is minus VC e to the minus T over RC. Then you bring down the -1 over RC. There it is. The C's go away, and we have V over R e to the minus T over RC, where V over R is the initial maximum current. So this is I is equal to I0 e to the minus t over RC. When t is equal to 0, I is equal to its maximum value I0. When t goes toward infinity, this goes to 0, I approaches 0, just like we would expect. All right, now what is the current? When the time that we're looking at the current equals RC. R times C is a certain value. Stick that in for t. Well, it's got a special relationship to this because it makes this whole thing just to the -1 power. So I is I0 e to the -1, which is I0 over e, which is 0.368 I0. Now what's the charge? The charge is Q times 1 minus the 1 over e, and that is 0.632. What do you think you get when you add this plus this? That's right, you get 1. Now, let's graph the current and the charge. So we're going to look especially at this particular value of time, RC. And the initial current starts at whatever level it is and diminishes down, asymptotically approaching 0, passing through this point here, which is 0.368 of the maximum. And then the charge, conversely, instead of diminishing, is building up rapidly. Okay, so the current is diminishing rapidly at first and then levels out. The charge is increasing rapidly at first and levels out. And so the value at RC is, 1 RC time constant, is 0.632 Q. So I already gave it away. RC is known as the time constant of the circuit. Really, it's a measure of the speed of the circuit. Symbol tau, just R times C. It tells you, if you multiply that together, how much time it takes to diminish to 0.368 of its maximum value, or to increase to 0.632 of its maximum value, depending on which way you're looking at it. So that's the RC time constant. It gives you a measure of the speed of the circuit, which is an important engineering term when you consider electronic circuits, for instance, computers, for instance, radio frequency circuits to produce transmitters and receivers and such things as that. So there is a good introduction to the RC circuit.